So thank you very much, especially to Tuan, of course, and for inviting me. And thanks, Phil. That was a wonderful talk. And just view this talk basically as a continuation, at least on the experimental side. It really builds on your groundbreaking setup that you rigged together in a day, it seems. So this is work done at the Advanced Light Imaging Spectroscopy Facility with a bunch of talented folks from Duke Arts and Sciences, Medical Center, and Calvert-Durham, which is a local community organization. So I don't have to convince you anymore about the importance of masks. They were so important and will be important to curb the spread. As you guys know, there are standards for masks, but of course, these mask standards focus primarily on the material itself. So if you clamp a piece of material between two funnels here, that behaves very differently from an actual mask on a real person. I mean, as you just heard, they're speaking, sneezing, coughing. Fluids behave differently from little salt particles. There's imperfect fits. There's different people have different faces, right? So, and even if you're lucky enough to get a mask tested, and they're expensive. These mask tests, they come with a certificate, but still they're in really high demand, and it's really hard to get them. And it might not tell you what you wanted it to tell. So really, this builds upon what you've just seen that came out of Professor Antonutz's lab at the NIH. So that was done in April, and we just seen the timeline. And in May, a now collaborator came to us, a person from Dr. Westman from the Medical Center. He's involved in Calvert-Durham, and he wanted to buy a bunch of masks and distributed them to the local community, but he had no idea whether these masks actually worked. So we figured, well, this paper just came out and showed beautifully with very simple techniques that there's lots of particles floating around when you talk. Can we just slap a mask on and see what effect that mask has on those emitted droplets? And that's exactly what we did. So in May, we went to the lab, and in fact, this was during the lockdown, so it was not before, it was during, and it took quite some convincing to let us, on the university side, to let us go into the lab in the first place. I didn't have a machinist, and I couldn't take a student because of social distancing rules. So I was lucky enough that my daughter volunteered to help out, and she's in the same household. I actually convinced the university that it's safe. So we went in there, set this up. So we used a laser, just like you've seen before. We shine it in the box, just same thing. I used an Android instead of my iPhone. We had a high precision cut hole for a face with a mask on. Of course, we were not the only ones doing experiments on masks. You've seen a beautiful talk by Dr. Kala this morning, and they all tried to help because there really wasn't any good information out there, right, on what mask actually helps. Plenty of people tried to get masks, they couldn't, so they would manufacture masks, they would sell masks that really it was not clear how much they actually helped. Okay, back to the lab. So we've extended this as well. So we added stay healthy people to add some more explosive sounds to it. And I'm gonna skip over the video. You've seen beautiful things, beautiful camera rolls before. What I'd rather show you is sort of an integrated picture of all the frames in the video when we said stay healthy people 5 times in a row. And this is our baseline. So basically no mask. So all the particles that come out of your mouth when you speak are integrated. You see a ton of them, big ones, small ones of all sizes, shapes and sizes. When you put a surgical mask on, most of those disappear. And that's, I mean, if you listened to the talk before, that's not surprising, right? With a sort of a cotton mask, garden variety cotton mask, it does reasonably well, not quite as well as a surgical mask, but it visibly reduces the emission. One Surprising result was we took a neck gaiter, slapped that on, and it didn't do well at all. And I'm going to come back to this a little bit more quantitative. So we analyzed these particles frame by frame and drew up a droplet emission as a function of time. And you see these 5 spikes. That's what the 5 sentences stay healthy people. And you see these 5 spikes, and then eventually the particles get cleared out of the box. And if you slap on a mask, so in this case, we took the bandana, you don't see it very well here, but these peaks, they decrease and they smear out as you would expect. And when you put on the cotton mask, it's really hard to see in the scale, but it's substantially reduced. What we, of course, really care about is the total number of particles. That's this shaded area here. And what we did to make this a little more quantitative, we took the number of particles, the total number of particles, and divided it by our baseline, which is no mask. So that gives us a relative droplet count. Okay, these are the masks that we happen to have lie around. This was really a development of the technique rather than in systematic mask tests. So we just took the ones we had available. So this is a surgical mask. You've seen these before. Here down here is the fitted N95 mask. So really clamps on your face, nothing really goes through. It was an advertised N95 mask. This is this knitted mask. This was actually the mask in question. A bunch of propylene mask, a cotton mask. We also had this neck gaiter that we found. We had a bunch of bandanas. So these are the kind of things we slapped on just to demonstrate that this technique actually can characterize masks. Here's what we found. This is a data set from one person testing all of these masks. And each run was done 10 times. That's why there are arrow bars on here. The relative droplet count, so 0 means nothing gets through the mask, everything's blocked. And 1 here, this is our reference here, this is no mask. Okay, so for some of those masks, we had actually a few of them lying around. So we did a test with 4 speakers just to get a little bit better statistics. And as you can tell, it's a little bit more varied as to be expected. So what can you see here? So obviously the fitted N95 mask, it's basically 0. So we really couldn't detect anything coming out of that mask. So that's really our gold standard. There's the surgical mask, which did pretty well. And again, of course, there's variability. Different people put it on differently. There's a little nose clip that might or might not fit. You might have a beard, maybe not. So, but overall, these masks down here, they did really well. The majority of masks worked pretty well. And keep in mind, this is, so 0.2 means 80% of the droplets are actually blocked. So that goes a long way, right? So what else can we see? You might wonder about this N95 mask here. Why is this so much worse? This is an N95 mask. Well, so first of all, just because it says it's an N95 doesn't mean it's an actual N95. There's lots of masks advertised out there that really don't perform the way they should. There's no certificate that come with that mask. In addition, it actually had this air valve here, which lets air escape when you exhale, and it shuts off when you inhale, which is great when it comes to protecting the wearer, because all the air that you inhale is filtered. However, it lets out unfiltered air, which of course is not so hot if you happen to have a virus and you look at the people around you. Another thing is, well, some of those masks didn't do too well. This is a knitted mask in question, didn't do so hot, and neither did the bandana. So bandana, of course, is really not a true face mask. There's lots of gaps, and even though we doubled it up, it still had a pretty decent transmission. The really surprising thing, of course, is this thing in the back corner here. What's up with that neck gaiter? Well, so if you look at the images that I showed you and zoom in a little bit, you kind of see what's going on. This is no mask case. You see those particles, there are tons of them. They're pretty big. They're small ones too. The neck gaiter, what you notice here is the big ones basically are gone, but there's tons of little ones, little droplets. So our explanation for this was that this thin fabric, this was a single layer thin fabric neck gaiter that we had lying around. We think it basically breaks up some of those big particles into little particles. And as you've just heard, those could potentially linger around for quite a while. Whereas really big particles, you might be lucky and they just drop to the ground. So we basically achieved our aim of developing this methodology, and we had hoped that, well, other people will pick up on this. It's really easy to build. It's one element, one optical element. So we figured, okay, let's get this out there. So we published this in Science Advances, and it was pretty quick as well. We were really not prepared for what happened afterwards. This went online on August 7th. In the same month, this has been viewed 1.5 million times, 300,000 PDF downloads. This puts everything else to shame. All the other papers I've ever written by far puts that to shame. Altmetric scores went through the roof. This is basically a measure of news coverage, and it made it into the top 30 papers of all time. This was absolutely crazy. We made it to the front page of several major news outlets. And I guess we weren't bound by the NIH rule at this point either. And by the way, I circled me just in case you couldn't figure out who the other people who were here. Also, funny enough, I guess the office of the vice president, they maybe gave up by this point, or they slept through this, I'm not sure. But CNN interviews actually did happen, and more than once. So this went totally crazy. So why in the world was that such a big deal? Well, for once, one thing is there was little information out there, right? I mean, people were starving for any sort of guidance. Do those masks work? Which ones work? But that was only part of the story. If you look at these headlines, it basically tells you what the problem was. It says, worse than going maskless. And this refers to our study. Well, this is not at all what we said in our study, not even close, right? So this really wasn't the point. So many science reporters or editors who made these headlines really didn't bother reading this thing in the first place. So some of them got it right. Well, this obviously was a development effort. So inexpensive, accessible device produces visual proof. That mask drop problem. Perfect. That's exactly what the paper said. Not surprisingly, we did not make any friends in the gaiter business. I've got hate mail from gaiter manufacturers. And this was that it ended up as Gaitergate. And I really recommend Google Gaitergate and look at some of those articles. They're really instructive. They tell you how this all came about. We've worked really hard to try to correct some of those headlines, of course, which was a real uphill battle. I do want to read one quote here. You as readers share the same responsibility we as publishers, including the editors, do. Vet all information thoroughly before drawing any conclusions. Nice thought. Fat chance. Anyway. So lots of times I figured, I asked myself the questions, could we have avoided some of this misinterpretation that's out there? And this is the published figure. This was really the core of the paper. And so yes, admittedly, it might have been a little too many colors. Maybe the legend wasn't quite clear enough. So we could have done something like this. Scale back the colors, put figures on there to make it a little clearer. But I think to really prevent this, the only thing that would have helped is warning labels all over the figure. Caution, limited statistics, results may vary with materials, number of layers, speakers, and so on, right? However, the Science Advances editors probably would have been less than thrilled seeing a figure like this. Anyway, that's a discussion for another talk. I do want to come back to this business of breakup. So one good thing about Gaitergate was it actually did prompt some scientific discussion. We were notified. Well, actually, it was a Twitter feed really that this breakup idea, really that shouldn't happen. And those were experts in the field. They claimed that, oh, this breakup is just not going to be happening under normal conditions. This is impossible. This must be small mask fragments that are created when we speak and we move the mask and this mask breaks down. And well, certainly that might be a contribution to this. However, in either case, these particles, whether they're really particles that break down or whether they're particles from the mask fragments, they're contaminated in either case. So it really doesn't matter. They're dangerous, and it's not a good thing. And by the way, I was very thrilled to see a publication that came out not too long ago that studied a thin mask and shot particles at it, and under reasonable condition, and voila, it actually shows a ton of little particles breaking apart. So this idea that we had initially wasn't really that crazy to start with. Anyway, this was a very simple technique, right? Simplicity obviously has limitations. So we don't see the particles that are smaller than about half a micron. That can be overcome. Also, even though we see half a microparticles, we can't actually measure them. We can't measure the size of it. That too, we could in principle fix. The one questions that we often got was, can you tell the difference whether these particles came through the mask or whether they came around the mask? So no, in our current design, we could not. We have a mix of both because the mask was actually well within the area of the box. So some of the particles that came out the side would be measured, some of them would not be. So this, of course, again, can be improved, but we could not distinguish particles from where they came from. Okay, so I'm getting warning messages here from Warren already to wrap it up. So there's the key of this setup really was its simplicity. This is the first time I've set up an optical experiment with one optical element. Well, the mirror was optional just for convenience. One cylindrical lens. This is super simple. So we used, of course, a really, really fancy pump laser for our green laser, but that's just because we had it standing around. You could easily use a really big fat laser pointer. I wouldn't call them pointer, but there are handheld 2-watt lasers out there that you can get for about $150. And it's really, the key is to get this out to the community. It's easy to replicate. And we've gotten tons of emails. I've spent literally 3 months answering emails. A good portion of this giving tips on how to replicate this experiment for manufacturing, transportation, museums, high schools, anything. This really is simple to set up. One case I do want to point out that I think was pretty cool. The tinkerers in you, off you will maybe know Adafruit is basically, you can buy little Raspberry Pis and Arduinos and all this kind of stuff. They have a little section on how to build your face mask efficiency test. So they actually tried this with a laser pointer, and the 100 milliwatt laser pointer they got for $45. The whole thing total was $200. That includes a camera and the analysis computer because it's done by a little Raspberry Pi. They actually did some quick tests and they found out that, well, not surprisingly, the bandana didn't do too well, but most other masks did just fine. Very much in line with what we saw. And I did really appreciate the warning label here. Be sure to wear proper eye protection. Keep in mind, these 100 milliwatt lasers are way more than your standard laser pointer. They're usually 5 milliwatts. So you can easily shoot somebody's eye out. So be careful with that. Anyway, in summary, I hope to have shown you that this was a very simple and easy experiment. It made humongous waves. And of course, I did not have a pre-pandemic slide in here either. this is not really what we do. We're microscopists in the chemistry and physics department. We deal with nonlinear light scattering and things like that. That was basically just trying to help out the community, trying to help out people, and it was a heck of a lot of fun.